Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You have recently developed a custom model for image classification by using a neural network. You need to automatically identify the values for learning rate, number of layers, and kernel size. To do this, you plan to run multiple jobs in parallel to identify the parameters that optimize performance. You want to minimize custom code development and infrastructure management. What should you do? The options are: Option A, train an AutoML image classification model. Option B, create a custom training job that uses the Vertex AI Vizier SDK for parameter optimization. Option C, create a Vertex AI hyperparameter tuning job. Option D, create a Vertex AI pipeline that runs different model training jobs in parallel.
To arrive at the correct answer, we focus on the keywords: automatically identify the values for learning rate, number of layers, and kernel size, run multiple jobs in parallel, minimize custom code development and infrastructure management.
The correct answer is option C, create a Vertex AI hyperparameter tuning job.
Why is this correct? C. Vertex AI hyperparameter tuning jobs automatically manage the infrastructure and orchestration needed to run multiple trials in parallel to find optimal hyperparameters, like learning rate, layers, and kernel size, with minimal custom code, perfectly satisfying the requirements. Why are the others incorrect? A. You already developed a custom model, so training a new AutoML model ignores your existing code and doesn't tune the specific neural network you just built. B. Using the Vertex AI Vizier SDK requires significant custom code development to orchestrate the trials, evaluate results, and manage the optimization loop, violating the requirement to minimize custom code. D. Manually creating a Vertex AI pipeline to run parallel jobs requires significant custom code and effort to implement the search algorithm and track the best parameters, which a hyperparameter tuning job handles natively.
You work for a bank. You have been asked to develop an ML model that will support loan application decisions. You need to determine which Vertex AI services to include in the workflow. You want to track the model's training parameters and the metrics per training epoch. You plan to compare the performance of each version of the model to determine the best model based on your chosen metrics. Which Vertex AI services should you use? The options are: Option A, Vertex ML Metadata, Vertex AI Feature Store, and Vertex AI Vizier. Option B, Vertex AI Pipelines, Vertex AI Experiments, and Vertex AI Vizier. Option C, Vertex ML Metadata, Vertex AI Experiments, and Vertex AI TensorBoard. Option D, Vertex AI Pipelines, Vertex AI Feature Store, and Vertex AI TensorBoard.
To arrive at the correct answer, we focus on the keywords: track the model's training parameters, metrics per training epoch, compare the performance of each version of the model.
The correct answer is option C, Vertex ML Metadata, Vertex AI Experiments, and Vertex AI TensorBoard.
Why is this correct? C. Vertex ML Metadata tracks artifact lineage, Vertex AI Experiments logs parameters and compares model versions, and Vertex AI TensorBoard visualizes metrics per training epoch. These services directly fulfill the requirements. Why are the others incorrect? A. Vertex AI Feature Store serves machine learning features, and Vertex AI Vizier optimizes hyperparameters. Neither tracks per epoch metrics or compares model versions. B. Vertex AI Pipelines orchestrates ML workflows, and Vertex AI Vizier performs hyperparameter tuning. They do not fulfill the requirement to track metrics per training epoch. D. Vertex AI Pipelines orchestrates workflows and Vertex AI Feature Store manages features. They do not track training parameters or compare model versions.
You work for a toy manufacturer that has been experiencing a large increase in demand. You need to build an ML model to reduce the amount of time spent by quality control inspectors checking for product defects. Faster defect detection is a priority. The factory does not have reliable Wi-Fi. Your company wants to implement the new ML model as soon as possible. Which model should you use? The options are: Option A, AutoML Vision Edge Mobile High Accuracy 1 model. Option B, AutoML Vision Edge Mobile Low Latency 1 model. Option C, AutoML Vision model. Option D, AutoML Vision Edge Mobile Versatile 1 model.
To arrive at the correct answer, we focus on the keywords. Faster defect detection is a priority. The factory does not have reliable Wi-Fi. Implement the new ML model as soon as possible.
The correct answer is option B, AutoML Vision Edge Mobile Low Latency 1 model.
Why is this correct? B. AutoML Vision Edge provides offline inference, solving the lack of reliable Wi-Fi, and the Mobile Low Latency 1 model directly addresses the priority for faster defect detection. Why are the others incorrect? A. The Mobile High Accuracy 1 model trades speed for accuracy, violating the explicit requirement that faster defect detection is a priority. C. The standard AutoML Vision model requires cloud connectivity for inference, which is unsuitable because the factory lacks reliable Wi-Fi. D. The Mobile Versatile 1 model is a compromise between speed and accuracy, but since faster detection is the main priority, the low latency model is optimal.
You are training and deploying updated versions of a regression model with tabular data by using Vertex AI pipelines, Vertex AI training, Vertex AI experiments, and Vertex AI endpoints. The model is deployed in a Vertex AI endpoint, and your users call the model by using the Vertex AI endpoint. You want to receive an email when the feature data distribution changes significantly, so you can retrigger the training pipeline and deploy an updated version of your model. What should you do? The options are: Option A, use Vertex AI model monitoring. Enable prediction drift monitoring on the endpoint, and specify a notification email. Option B, in cloud logging, create a logs-based alert using the logs in the Vertex AI endpoint. Configure cloud logging to send an email when the alert is triggered. Option C, in cloud monitoring, create a logs-based metric and a threshold alert for the metric. Configure cloud monitoring to send an email when the alert is triggered. Option D, export the container logs of the endpoint to BigQuery. Create a cloud function to run a SQL query over the exported logs and send an email. Use Cloud Scheduler to trigger the cloud function.
To arrive at the correct answer, we focus on the keywords: tabular data, Vertex AI endpoint, receive an email when the feature data distribution changes significantly.
The correct answer is option A, use Vertex AI model monitoring. Enable prediction drift monitoring on the endpoint, and specify a notification email.
Why is this correct? A. Vertex AI model monitoring natively supports tabular data on Vertex AI endpoints to detect prediction drift, feature data distribution changes, and can be configured to send email notifications directly. Why are the others incorrect? B. Cloud logging captures application logs and can alert on log patterns, but it cannot natively compute statistical changes in feature data distributions, prediction drift. C. Cloud monitoring is used for tracking system metrics and logs. It does not have built-in statistical capabilities to analyze feature data distribution changes. D. Building a custom solution with BigQuery and Cloud Functions is an unnecessary operational overhead, as Vertex AI model monitoring provides this exact functionality natively.
You are working on a prototype of a text classification model in a managed Vertex AI Workbench notebook. You want to quickly experiment with tokenizing text by using a Natural Language Toolkit (NLTK) library. How should you add the library to your Jupyter kernel? The options are: Option A, install the NLTK library from a terminal by using the pip install NLTK command. Option B, write a custom Dataflow job that uses NLTK to tokenize your text and saves the output to cloud storage. Option C. Create a new Vertex AI Workbench notebook with a custom image that includes the NLTK library. Option D. Install the NLTK library from a Jupyter cell by using the pip install NLTK user command.
To arrive at the correct answer, we focus on the keywords, Managed Vertex AI Workbench Notebook, quickly experiment, add the library to your Jupyter kernel.
The correct answer is option D. Install the NLTK library from a Jupyter cell by using the pip install NLTK user command.
Why is this correct? D. Installing the library directly from a Jupyter cell using the pip command with the user flag is the quickest way to add a package to the active kernel without requiring a restart. Why are the others incorrect? A. Installing from a terminal adds the package to the environment but may require a kernel restart to make it available for use in the active notebook session. B. Creating a custom Dataflow job introduces unnecessary complexity and overhead, making it unsuitable for rapid, interactive experimentation within a notebook. C. Building a custom container image and provisioning a new notebook instance is extremely time-consuming and overkill for simply experimenting with a standard library.
You are working on a neural network-based project. The dataset provided to you has columns with different ranges. While preparing the data for model training, you discover that gradient optimization is having difficulty moving weights to a good solution. What should you do? The options are: Option A, use feature construction to combine the strongest features. Option B, use the representation transformation, normalization, technique. Option C, improve the data cleaning step by removing features with missing values. Option D, change the partitioning step to reduce the dimension of the test set and have a larger training set.
To arrive at the correct answer, we focus on the keywords, columns with different ranges, gradient optimization is having difficulty moving weights to a good solution.
The correct answer is option B. Use the representation transformation, normalization, technique.
Why is this correct? B. Normalization scales features to a common range, preventing variables with larger scales from dominating the loss function. This ensures smoother, more stable, and faster convergence during gradient optimization for neural networks. Why are the others incorrect? A. Feature construction creates new features from existing ones. This does not address the root cause of convergence issues, which is the vastly different numerical scales of the input columns. C. Handling missing values improves data quality but does not solve the scaling problem. Gradient optimization will still struggle if the retained features have different numerical ranges. D. Adjusting train/test split sizes impacts model evaluation and learning capacity, but it fails to resolve the mathematical convergence issues caused by features having unscaled, varying ranges.
You work for the AI team of an automobile company, and you are developing a visual defect detection model using TensorFlow and Keras. To improve your model performance, you want to incorporate some image augmentation functions such as translation, cropping, and contrast tweaking. You randomly apply these functions to each training batch. You want to optimize your data processing pipeline for runtime and compute resources utilization. What should you do? The options are: Option A, embed the augmentation functions dynamically in the TF data pipeline. Option B, embed the augmentation functions dynamically as part of Keras generators. Option C, use Dataflow to create all possible augmentations and store them as TF records. Option D, use Dataflow to create the augmentations dynamically per training run and stage them as TF records.
To arrive at the correct answer, we focus on the keywords, TensorFlow and Keras, image augmentation functions, randomly apply these functions to each training batch, optimize your data processing pipeline for runtime and compute resources utilization.
The correct answer is option A. Embed the augmentation functions dynamically in the TF data pipeline.
Why is this correct? A. Embedding augmentation dynamically in the TF data pipeline optimizes runtime and compute resources by allowing fast, parallelized CPU execution in C++ instead of Python. Why are the others incorrect? B. Keras generators execute in Python and suffer from global interpreter lock, GIL, limitations, making them significantly slower and less efficient than TF data. C. Pre-computing and storing all possible augmentations as TF records is highly inefficient for storage resources and severely limits the randomness of transformations. D. Creating augmentations dynamically with Dataflow per training run introduces massive latency and compute overhead, conflicting with the goal of optimizing runtime.
You work on the data science team for a multinational beverage company. You need to develop an ML model to predict the company's profitability for a new line of naturally flavored bottled waters in different locations. You are provided with historical data that includes product types, product sales volumes, expenses, and profits for all regions. What should you use as the input and output for your model? The options are: Option A, use latitude, longitude, and product type as features. Use profit as model output. Option B, use latitude, longitude, and product type as features. Use revenue and expenses as model outputs. Option C, use product type and the feature cross of latitude with longitude, followed by binning, as features. Use profit as model output. Option D, use product type and the feature cross of latitude with longitude, followed by binning, as features. Use revenue and expenses as model outputs.
To arrive at the correct answer, we focus on the keywords: predict the company's profitability, different locations, product types.
The correct answer is option C, use product type and the feature cross of latitude with longitude, followed by binning, as features. Use profit as model output.
Why is this correct? C. Crossing latitude and longitude followed by binning creates spatial grids that effectively capture location-based patterns. Since the objective is predicting profitability, profit is the direct and most appropriate single-target variable. Why are the others incorrect? A. Using raw latitude and longitude as continuous features is ineffective because their relationship to the target is nonlinear. Spatial data requires crossing and binning. B. Raw geographic coordinates fail to capture regional nuances effectively. Furthermore, predicting both revenue and expenses adds unnecessary complexity when the direct objective is profitability. D. While the spatial features are correctly pre-processed via crossing and binning, predicting revenue and expenses as multiple outputs complicates the model unnecessarily instead of directly predicting profitability.
You work for a retail company that is using a regression model built with BigQuery ML to predict product sales. This model is being used to serve online predictions. Recently, you developed a new version of the model that uses a different architecture, custom model. Initial analysis revealed that both models are performing as expected. You want to deploy the new version of the model to production and monitor the performance over the next 2 months. You need to minimize the impact to the existing and future model users. How should you deploy the model? The options are: Option A, import the new model to the same Vertex AI model registry as a different version of the existing model. Deploy the new model to the same Vertex AI endpoint as the existing model, and use traffic splitting to route 95% of production traffic to the BigQuery ML model and 5% of production traffic to the new model. Option B, import the new model to the same Vertex AI model registry as the existing model. Deploy the models to one Vertex AI endpoint. Route 95% of production traffic to the BigQuery ML model and 5% of production traffic to the new model. Option C, import the new model to the same Vertex AI model registry as the existing model. Deploy each model to a separate Vertex AI endpoint. Option D, deploy the new model to a separate Vertex AI endpoint. Create a Cloud Run service that routes the prediction requests to the corresponding endpoints based on the input feature values.
To arrive at the correct answer, we focus on the keywords, serve online predictions, deploy the new version of the model to production, monitor the performance, minimize the impact to the existing and future model users.
The correct answer is option A. Import the new model to the same Vertex AI model registry as a different version of the existing model. Deploy the new model to the same Vertex AI endpoint as the existing model, and use traffic splitting to route 95% of production traffic to the BigQuery ML model and 5% of production traffic to the new model.
Why is this correct? A. This correctly leverages Vertex AI model registry's versioning. Deploying the new version to the same endpoint and using traffic splitting allows for canary testing, minimizing impact to users while monitoring production performance natively. Why are the others incorrect? B. While it mentions traffic splitting, it fails to explicitly specify importing the new model as a different version of the existing model, which is the standard organizational practice in Vertex AI model registry. C. Deploying to a separate endpoint would require modifying client applications to manage traffic routing, which directly violates the requirement to minimize the impact on existing model users. D. Building a custom cloud run service to route traffic adds unnecessary architectural complexity and operational overhead, especially since Vertex AI endpoints natively support traffic splitting.
You work for a social media company. You want to create a no-code image classification model for an iOS mobile application to identify fashion accessories. You have a labeled dataset in cloud storage. You need to configure a training workflow that minimizes cost and serves predictions with the lowest possible latency. What should you do? The options are: Option A, train the model by using AutoML, and register the model in Vertex AI model registry. Configure your mobile application to send batch requests during prediction. Option B, train the model by using AutoML Edge and export it as a core ML model. Configure your mobile application to use the .ml model file directly. Option C, train the model by using AutoML Edge and export the model as a TF-Lite model. Configure your mobile application to use the .flight file directly. Option D, train the model by using AutoML and expose the model as a Vertex AI endpoint. Configure your mobile application to invoke the endpoint during prediction.
To arrive at the correct answer, we focus on the keywords: no-code image classification model, iOS mobile application, minimizes cost, lowest possible latency.
The correct answer is option B, train the model by using AutoML Edge and export it as a core ML model. Configure your mobile application to use the .ml model file directly.
Why is this correct? B. AutoML Edge enables no-code edge model training. Exporting as core ML is the native solution for an iOS mobile application, ensuring on-device inference which achieves the lowest possible latency and minimizes cost by eliminating server-side prediction charges. Why are the others incorrect? A standard AutoML with Vertex AI model registry and batch requests incurs ongoing server costs and high latency, failing to meet the lowest possible latency and cost minimization requirements. C. While TF-Lite can run on iOS, Core ML, .ml model is Apple's native framework for iOS mobile applications, making it the most optimized and standard choice over TF-Lite for iOS edge devices. D. Serving predictions via a Vertex AI endpoint requires network round trips, significantly increasing latency and incurring ongoing API costs, rather than minimizing cost and latency.
You have trained an XGBoost model that you plan to deploy on Vertex AI for online prediction. You are now uploading your model to Vertex AI model registry, and you need to configure the explanation method that will serve online prediction requests to be returned with minimal latency. You also want to be alerted when feature attributions of the model meaningfully change over time. What should you do? The options are: Option A, 1. Specify sampled Shapley as the explanation method with a path count of 5.2. Deploy the model to Vertex AI endpoints. 3. Create a model monitoring job that uses prediction drift as the monitoring objective. Option B, 1. Specify integrated gradients as the explanation method with a path count of 5.2. Deploy the model to Vertex AI endpoints. Point 3. Create a model monitoring job that uses prediction drift as the monitoring objective. Option C. 1. Specify sampled Shapley as the explanation method with a path count of 50.2. Deploy the model to Vertex AI endpoints. Point 3. Create a model monitoring job that uses training serving skew as the monitoring objective. Option D. 1. Specify integrated gradients as the explanation method with a path count of 50.2. Deploy the model to Vertex AI endpoints. Point 3. Create a model monitoring job that uses training serving skew as the monitoring objective.
To arrive at the correct answer, we focus on the keywords: XGBoost model, explanation method, minimal latency, feature attributions, change over time.
The correct answer is option A. 1. Specify sampled Shapley as the explanation method with a path count of 5.2. Deploy the model to Vertex AI endpoints. Point 3. Create a model monitoring job that uses prediction drift as the monitoring objective.
Why is this correct? A. Sampled Shapley is the recommended explanation method for tree-based models like XGBoost. A lower path count of 5 minimizes latency. Monitoring prediction drift detects when feature attributions change over time in live serving data. Why are the others incorrect? B. Integrated gradients is designed for differentiable models like neural networks, not tree-based models like XGBoost. C. A path count of 50 would increase latency, and training serving skew compares serving data to a training baseline rather than detecting changes over time. D. Integrated gradients is not used for XGBoost models, a path count of 50 increases latency, and training serving skew does not monitor data changes over time.
You work for a textile manufacturing company. Your company has hundreds of machines, and each machine has many sensors. Your team used the sensory data to build hundreds of ML models that detect machine anomalies. Models are retrained daily, and you need to deploy these models in a cost-effective way. The models must operate 24/7 without downtime and make sub-millisecond predictions. What should you do? The options are: Option A, deploy a Dataflow batch pipeline and a Vertex AI prediction endpoint. Option B, deploy a Dataflow batch pipeline with the Run-Inference API and use model refresh. Option C, deploy a Dataflow streaming pipeline and a Vertex AI prediction endpoint with autoscaling. Option D, deploy a Dataflow streaming pipeline with the Run-Inference API and use automatic model refresh.
To arrive at the correct answer, we focus on the keywords: models are retrained daily, cost-effective way, operate 24/7 without downtime, sub-millisecond predictions.
The correct answer is option D. Deploy a Dataflow streaming pipeline with the Run-Inference API, and use automatic model refresh.
Why is this correct? D. A Dataflow streaming pipeline ensures 24/7 operation. The Run-Inference API enables cost-effective, sub-millisecond predictions by avoiding network latency. Automatic model refresh handles daily retrained models without downtime. Why are the others incorrect? A. A batch pipeline cannot operate 24/7 for streaming data. Vertex AI prediction endpoints introduce network latency, missing the sub-millisecond requirement, and are not cost-effective for hundreds of models. B. A batch pipeline processes bounded data and stops, failing the requirement to operate continuously 24/7 without downtime for sensor data. C. While streaming supports 24/7 operation, Vertex AI prediction endpoints add network latency, failing the sub-millisecond requirement, and are less cost-effective than run inference for hundreds of models.
You created a model that uses BigQuery ML to perform linear regression. You need to retrain the model on the cumulative data collected every week. You want to minimize the development effort and the scheduling cost. What should you do? The options are: Option A, use BigQuery's scheduling service to run the model retraining query periodically. Option B, create a pipeline in Vertex AI pipelines that executes the retraining query, and use the Cloud Scheduler API to run the query weekly. Option C. Use Cloud Scheduler to trigger a cloud function every week that runs the query for retraining the model. Option D. Use the BigQuery API connector and Cloud Scheduler to trigger workflows every week that retrains the model.
To arrive at the correct answer, we focus on the keywords, uses BigQuery ML, retrain the model every week, minimize the development effort and the scheduling cost.
The correct answer is option A, use BigQuery's scheduling service to run the model retraining query periodically.
Why is this correct? A. BigQuery's built-in scheduling service natively automates query execution without requiring external orchestration tools, which minimizes both development effort and operational costs. Why are the others incorrect? B. Vertex AI pipelines adds unnecessary architectural complexity and incurs additional costs, failing the requirement to minimize development effort and scheduling costs. C. Creating a cloud function requires writing and maintaining custom code, increasing development overhead compared to using native BigQuery scheduled queries. D. Using workflows adds unnecessary orchestration layers and complexity for a single query execution, increasing development effort and cost over native scheduling.
You are developing a recommendation engine for an online clothing store. The historical customer transaction data is stored in BigQuery and cloud storage. You need to perform exploratory data analysis, EDA, pre-processing, and model training. You plan to rerun these EDA, pre-processing, and training steps as you experiment with different types of algorithms. You want to minimize the cost and development effort of running these steps as you experiment. How should you configure the environment? The options are: Option A. Create a Vertex AI Workbench user-managed notebook using the default VM instance, and use the %% BigQuery magic commands in Jupyter to query the tables. Option B. Create a Vertex AI Workbench managed notebook to browse and query the tables directly from the Jupyter Lab interface. Option C. Create a Vertex AI Workbench user-managed notebook on a Dataproc hub, and use the %% BigQuery magic commands in Jupyter to query the tables. Option D. Create a Vertex AI Workbench managed notebook on a Dataproc cluster, and use the Spark BigQuery connector to access the tables.
To arrive at the correct answer, we focus on the keywords, stored in BigQuery and cloud storage, minimize the cost and development effort.
The correct answer is option B. Create a Vertex AI Workbench managed notebook to browse and query the tables directly from the Jupyter Lab interface.
Why is this correct? B. Vertex AI Workbench managed notebooks feature built-in integration with BigQuery and cloud storage, allowing you to browse and query tables directly from the Jupyter Lab interface, thereby minimizing development effort during EDA and experimentation. Why are the others incorrect? A. User-managed notebooks require more configuration and maintenance than managed notebooks, increasing development effort. Relying on magic commands is also less seamless than the built-in BigQuery interface provided by managed notebooks. C. Using Dataproc Hub introduces unnecessary complexity and cost for standard EDA and training tasks that do not explicitly require a Hadoop or Spark ecosystem. D. Provisioning a Dataproc cluster and using a Spark connector is excessive and more expensive for this scenario, which does not specify a need for large-scale distributed Spark processing.
Refer to the attached Picture 1, reference exhibit. You have developed an application that uses a chain of multiple scikit-learn models to predict the optimal price for your company's products. The workflow logic is shown in the diagram. Members of your team use the individual models in other solution workflows. You want to deploy this workflow while ensuring version control for each individual model and the overall workflow. Your application needs to be able to scale down to 0. You want to minimize the compute resource utilization and the manual effort required to manage this solution. What should you do? The options are: Option A. Expose each individual model as an endpoint in Vertex AI endpoints. Create a custom container endpoint to orchestrate the workflow. Option B. Create a custom container endpoint for the workflow that loads each model's individual files. Track the versions of each individual model in BigQuery. Option C. Expose each individual model as an endpoint in Vertex AI endpoints. Use Cloud Run to orchestrate the workflow. Option D. Load each model's individual files into Cloud Run. Use Cloud Run to orchestrate the workflow. Track the versions of each individual model in BigQuery.
To arrive at the correct answer, we focus on the keywords. Members of your team use the individual models in other solution workflows. Version control for each individual model, scale down to 0, minimize the compute resource utilization and the manual effort.
The correct answer is option C. Expose each individual model as an endpoint in Vertex AI endpoints. Use Cloud Run to orchestrate the workflow.
Why is this correct? C. Exposing models as Vertex AI endpoints enables easy versioning and independent reuse by team members. Orchestrating the chain with Cloud Run perfectly satisfies the requirement to scale down to 0, minimizing compute resources and manual management effort. Why are the others incorrect? A. Vertex AI endpoints do not natively scale down to 0 for custom container endpoints as efficiently as Cloud Run, which leads to unnecessary continuous compute resource utilization. B. Manually tracking model versions in BigQuery and loading files into a container drastically increases manual effort. It also hinders the independent reuse of models by other teams. Why are the others incorrect? D. Loading model files into Cloud Run prevents other teams from easily reusing the individual models via endpoints. Furthermore, tracking versions in BigQuery introduces significant manual effort.